Hello everybody. So this is going to be our first actual set of lecture notes for math or CPSC 7. So what we're going to be looking at is section 1.1 in the book. So this is from the textbook, right? Section 1.1 in the textbook. And so this PDF that I'm drawing on right now, you've had access to this PDF, but after I have this video done, I'm going to upload this annotated version that I've drawn over just in case you want it. So what this first section is going to be propositional logic. So you can take an entire class in propositional logic or symbolic logic here at Merced College. I know that because I took it forever ago, and I assume it still exists. So if I took it, you can take it. And we're only going to do a couple of sections of it. I think 2 sections of it, and that's going to be it for us. So what propositional logic is it's going to be the rules for how simple things like, if you say something and something, what's that mean? If you say something or something, what's that mean? If you say, if this is true, then this is true, what's that mean? And we need to have rigorous mathematical definitions of those things because we want to be able to write proofs, mathematical proofs, right? So we need these to understand and construct correct mathematical proofs. So when we write a proof of a theorem, a mathematical statement of fact, we want to be able to write a proof that proves the theorem, and we want to be able to say for sure that our proof is correct and it does in fact prove the theorem. So if we make a statement, you know, this fact or this thing is a fact and it's always true, then you know, we need a way to verify that. And so you can't do it without rules of logic, of course. And so that's what these sections are about, rules of logic. Okay, and so here's where we're going to start. All right, we're going to start with propositions, which is why this is called propositional logic, by the way. So propositions. So proposition is a declarative sentence. So when we say declarative sentence, what we mean is a sentence that declares a fact that is either true or false, but not both. Okay, so examples of propositions are what we have right here. So 1.2, 1 plus 2 equals 3 is a proposition because it's making a statement. You're claiming that 1 plus 2 is equal to 3, right? It's a claim. Now, it could be a false claim or a true claim. That doesn't matter. It doesn't matter whether it's true or false. The point is that you're making a statement that something is a fact, and it could be true or it could be false, but it is one of those, true or false. Okay, so it's making a statement. It is declaring a fact. So it's declaring that 1 plus 2 is equal to 3, right? So it is declaring a fact. In this case, it happens to be true, but that's not important. But that doesn't matter. Okay, so we're not asking whether it's true or not. We're asking whether or not it could be true or false. So the next one we've got on here is 1 plus 1 equals 17. Oops, crossed it out. 1 plus 1 equals 17. That's also a proposition, right? You're still declaring a fact. In this case, it's wrong. It's a false statement, but it's still a proposition, right? So this is similar to the one above. So this is still a declarative statement. So it's declaring 1 plus 1 is equal to 17. That happens to be false. Okay, that doesn't matter. It's still a proposition, right? And the others, I am 7 feet tall and Arkansas is a state. Those are also propositions. One of those is true and one of those is false. I'll let you try to figure out which one is true and which one is false. But these are all making statements of fact, right? Whether it's true or not is irrelevant. Okay, so in order for something to not be a proposition, if it's not a proposition, that means something went wrong. So what could go wrong? And actually we say it down here. So if something does not declare a fact, then it's not a proposition. And also, if it does declare a fact, but it can't have a value of true or false yet, then that would make it not a proposition as well. And I want to be clear here about this because it's a little bit tricky. So when I say it does declare facts, it says but aren't true or false until we know what the variables are. That's what's important. It's not that we don't know if it's true or false, right? You're not always going to know if a proposition is true or false, and it's still a proposition. So it's not the fact that we don't know, it's the fact that it's actually impossible to know, okay? Because of something having to do with the not a proposition thing. So I'll talk about that in a second. So let's just go over these. So these are statements that are not propositions. So right here, it says go to the store. Okay, not a proposition. Why? Because that's not a statement that declares a fact that's true or false, right? Not a statement that could be true or false. True or false. Okay, so it's not a proposition for that reason. Same thing here. How are we doing? Also not a statement of fact. Okay, so that's the problem with both of those. They don't actually claim a fact. Now, if I said you went to the store, or if I said you are going to the store, then that would be a proposition. If I say you are going to the store, that could be true if you are going to the store, or it could be false if you're not going to the store. But you are going to the store is still making a statement about a fact. Okay? But go to the store is not. You're telling somebody to go to a store. You're not claiming a fact. Same thing with how are we doing? How are we doing? Bad, but that's not the point. The point is that how are we doing is not a true or false statement. Okay? So it's just not a proposition. Now these others, these are what I'm talking about as far as things that aren't true or false. So these do declare facts, okay? So these two here do declare facts. So this one and this one, these declare facts. A fact that is true or false, so you think it's a proposition. But the problem is that they're not actually true or false until you know what x is, right? X has to have a value. So they declare a fact that's true or false, but only after you define the variables. So the x, the y, and the z. You have to have numbers in for the x, y, and z before it's true or false. So if you have not defined x, y, and z, then it's not actually true or false, right? Like whether or not x plus 1 equals 3 depends on x. So if nobody has defined x yet, then it can't possibly be true or false. So it can't be a proposition. So declare a fact is true or false, but only after you define x, y, and z. So until then, not a proposition. And something I want to say about this is that on the homework you're probably going to have to say whether or not something is a proposition, and you'll need to think about this. But after this section, you're not going to have to worry about it again. So don't get super hung up on these things. We only are interested in symbolic logic so that we can get to the point of proving theorems. So these really, really basic things are not things you have to worry about a lot. Anyway, so that's what a proposition is. So it's a declarative sentence. It says a fact, and doesn't have to be true, just has to be making a claim. Okay. Now, once we know what propositions are, what we're going to want to do is kind of use a shorthand for them. And so we're going to assign variable names to them. And so you see right here, it says usually PQRST. That's what we usually use to call our propositions. Okay. And then what you can do is you can assign a variable to a proposition, and then you don't have to write the words. Okay. And so like we say right here, it says Greg is 7 feet tall, and then we can assign it to the variable P, right? And then you could say, is P true or false, right? And you don't have to write out the words Greg is 7 feet tall anymore. You can just refer to it as P. Okay, so is P true or false? And of course the answer is false, because I'm Greg and I am not 7 feet tall. I am in fact what am I? A short person. Not that short. Not that tall though. Just a person. I was going to say something, but then I decided not to. I was going to say that I was a pygmy Sasquatch. So I don't know why I didn't say it, but then I did say it. Okay, compound propositions. Okay, now once you can define a proposition, right? So we know what a proposition is, and we've defined it as a variable, like a P, a Q, an R, an S, a T, etc. They can be anything, but we use PQRST. What we want to do then is we want to put them together, multiple propositions together to make a bigger proposition. Okay, and so that's what a compound proposition is. It's a proposition formed from one or more propositions combined with logical operators, right? And so what we're going to learn is all of the logical operators that you could have. Okay, so our first logical operator is going to be negation. So negation is well, literally the negation. It is what it says it is. So what you want to notice about it is, first of all, the notation, right? So the negation of P, we're going to use this symbol right here. Not P is how we'll typically say it. We'll say not P. Other books use this. We're not going to use that, okay? But it's there for like kind of completion. We're going to use the first one. And you can always write the negation of something by adding this, it is not the case that P. That's the negation. Okay, so as an example here, if I am asking you to find the negation of the statement Greg is 7 feet tall, you could write it just by adding those words, it is not the case that, in front. So you just say it is not the case that Greg is 7 feet tall. Okay, that's the negation. It is not the case that whatever it is. Now, when I say here that you should feel free to change the wording to make the English better, in fact, you need to be able to change the wording to make the English better, because some of the problems on the homework will specifically say, find the negation of the statement, do not use the words, it is not the case that. Okay, so even though technically you can always do that to find the negation, you're not actually going to be allowed to. So when you say it is not the case that Greg is 7 feet tall, you need to be able to rewrite that as just Greg is not 7 feet tall. That's the negation of Greg is 7 feet tall, right? So you should be able to use what you know about normal English language rules in order to come up with those negations, right? So Greg is not 7 feet tall. That's the negation. Okay. So like here we have this. Jen got at least 80% on the first exam. So again, you could write it, it is not the case that Jen got 80% on the first exam for the negation, right? Negation of that. But you wouldn't want to, right? That's not the best way to say it. If somebody said, you know, did you get at least 80% on the first exam, you would not answer, it is not the case that I got at least 80% on the first exam, right? That's not how you would say no. If you want to negate this, Jen got at least 80%, the negation, if you think about it, so the negation of this, how would you say not at least 80%? You would say below 80%, right? So you have at least 80% or you have below 80%. Those are the two choices. So if you want to negate at least 80%, the negation would be below 80%. So you could say it is not the case that Jen got at least 80%, but you should not, right? This is not the way you want to do it. You don't want to add, it is not the case that. You want to just say, well, I guess I said Jen didn't get at least 80%. Right, she did not. But then you say Jen got less than an 80%. So there's multiple ways to do that. And, you know, you need to pick one that sounds good, basically. And you want to try to avoid that it is not the case that wording, even though it is technically correct. Okay? Now, when we're talking about logical operators, you're going to need to be able to write truth tables for those logical operators. Okay, so what a truth table is it's a table, first of all, and in that table, you're going to keep track of all of the possible truth values for one or more propositions. Okay, so let me, well, I guess we can do this. It's right here, but I'll write one down here. So what a truth table looks like is this. So what you do is on top, you put whatever things you need to keep track of the truth values of. So like if we're doing P and not P and we need to make a truth table, what you would do is you would say, okay, well, we're going to do P and we're going to do not P. So that's what you put on the top. Okay, then what you do is for all of the propositions, not the compound propositions, right? So this is a compound proposition because of the not right there. That doesn't count. But for the regular propositions like this, what you want to do is you need every combination of true and false down here. And so you just label those. So the way I would label those is, well, what are the truth values that P could possibly have? So the truth values that P could have are true or false. Okay, so those are the possible truth values for P. So you put them right there. And then once you have the truth values of P, then you would say, okay, well, if the truth values of P are true and false, what are the truth values for not P, the negation of P? So we fill in the truth values for the compound statement. So we're just going to fill those in. And so what you would have to do is you would say, well, if P is true, what should not P be? The negation be? Well, the negation is going to simply flip the truth value to the other truth value. And same thing for this one. If P is false, the negation of P would actually be true. And that's it. That's the truth table right there. What we're doing there is this table is a complete list of how the negation operator works. Okay, so what this is supposed to be doing is the table describes how the negation operator works, right? You see that when you have something that's true and you apply the negation, it becomes false. And if you have something that's false and you apply the negation, it becomes true. Okay, and that's what a truth table is for. So if we go down here, we're just going to see the same truth table, right? True, false, and then false, true. Now, truth tables actually don't make very much sense when you're talking about the negation operator. They really start to make sense once you have what we call like, well, I was going to say compound propositions, but technically negation is a compound proposition. But they really start to make sense when you have compound propositions involving multiple propositions, right? So this is the first one we're going to see. So the first one we're going to see is going to be conjunction. And you do kind of need to remember this, conjunction, the name conjunction, just because the book will use it sometimes. But what conjunction means is just the and operator, the and operator. And so everybody reads it as and. Nobody ever says the conjunction of P and Q. They say P and Q. That's what they say. All right, and so you'll see that written right here. So what do we have? We have P and Q are both propositions. Conjunction, written this way. So this is the symbol for it. So it's like a triangle here, sort of. And the way I remember it is, because we're going to do the one for or in a second. So I don't know why this works, but so the way it was taught to me was like, that kind of looks like an N for and that was enough to make it make sense to me. Because the other one is like this, and that's or. But that doesn't look like anything to me, so I don't know. For some reason this idea worked, that you know, that's an N and that looks like an N. So it's like P and Q. P and Q. And that's how I remember them. So there's an and there's an or. Okay? And the definition here, this is the book definition straight from the book, tells you how it's supposed to work. So take a look at this. Conjunction is true when both P and Q are true, false otherwise. So probably down below here, there's going to be a truth table. There is, but I'm going to draw the truth table here and we'll learn how to draw it. Okay, so we're going to practice making a truth table here. So if we're trying to make a truth table for P and Q, so truth table for P and Q. So the way you would do that is, we're going to start out our table. You put a P, you put a Q, right? Because we know we have a P, we have a Q, and then after we have a P and a Q, then we're going to have the P and Q, like that. Okay, and what we need, remember what I said about the basic propositions? I said, like we did here for the true and the false, I said you need every combination or every possible outcome for true and false. And what we have to do here is we need every combination, every combo of true and false needs to be represented in this truth table. Because if you left one out, then we wouldn't know what happens. And this is supposed to be describing everything about how the and operator works. So what you do, and you need to do it this way, and I believe this is actually the opposite of what some computer science instructors do, but what I'm going to do matches what the book does and matches mostly what you'll see if you look stuff up online. So in order to get every combination of true and false, what you want to do is, first of all, if you have one proposition, one prop, that actually means there's going to be two rows in your truth table, right? Like 1, 2. If you have two propositions, there's actually going to be 4 rows to get every combination of true, false. If you have 3 propositions, it's going to take 8 rows. If you had 4 propositions, it would actually be 16 rows, right? It doubles every time. It's actually 2 to the n rows. And so what you do is when I'm doing 2 here, I know that with 2 propositions, that should be 4 rows of my truth table. And so what you do is you say, okay, well, I need 4 rows. And so for P, in order to get 4 rows, I know that 2 of them should be true and 2 of them should be false. Okay? So you go 2 true, 2 false. And then for the Q, 2 of those should be true and 2 of those should be false. But you write them this way: true, false, true, false. Okay? And if you follow this method, right, where we've got 2 and then 1, 1, 1, 1, that's going to get you every possible combination of true and false, right? If you don't believe me, you can look, right? Because we've got true, 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 false, false, true, false, false. And that's going to be every combination of true and false that you could get from 2 different choices. Okay, having done that much of the truth table, let's actually read what the definition says. So according to the definition here, conjunction is true when P and Q are true. So where are P and Q true? Here the P and Q are false. Here P is false, Q is true. Here P is true, Q is false. Here P is true, Q is true. So that's this, right? P and Q are true. So P and Q are true only on that top row. And so it says the conjunction is true when they're both true. So that's telling you that this should be filled in with a true. Okay? Now what else does it say? False otherwise. Now when they say otherwise, what they mean is every other combination is going to be false. So you come here and you say all of the others are false. Only true, true is true. Okay? And that's the truth table for conjunction. That's the truth table for and. Okay? The only time it's true is when both things are true. And it makes sense in terms of English. Do I have a place to write English? I'll write one up here and I'll erase it. But like, think about this. Like if I say, I have $20 and what else do I have? I have a milkshake. Why? I don't know. It's just what I thought of. Okay, if I say I have $20 and I have a milkshake, right? Then what I'm saying is this right here, that could be my P. This right here, I have a milkshake, that could be a Q. That's not a Q. What am I doing? That could be a Q. And then in the middle, you have an and. That's not what I'm trying to do here. In the middle, you have an and that's this, right? So P and Q. So when is that true? In order for this to be true, both of those need to be true. So this is only true. Only true if both I have $20 and I have a milkshake, are true, right? That's how conjunction works. That's how and works. So if you say A and B both need to be true for that to be true. And that's what this truth table shows. P and Q have to be true in order for P and Q to be true. That's and. Okay, now let's talk about disjunction. So disjunction is the statement or, right? So it says right here, P or Q, and this is the statement for or. We already talked about it. So that's the symbol for or. Now let's make the truth table. So again, I could come down below and make the truth table, but let's try to make the truth table. We'll try to fit it in right here. So I'll go P, Q, P or Q, and we'll see if we can read off the instructions and make our truth table without looking at the one below. Okay, so we need all of the combinations of true and false again. Now we're not thinking about it, we're just going to do the same thing we did last time. So you go true, true, false, false, and then you go true, false, true, false. Okay, don't think about it, just copy the pattern. All right, now let's read the instructions here. So it says P or Q false when P and Q are false. So where are P and Q false? Last row. And if that happens, if they're both false, P or Q is false. That tells me to put a false right here. All right, now what else? True otherwise. So otherwise means all of the other options. So all of the other options should be true. True, true, true. So that's your truth table for or. And if we look down here, we're going to just see the truth tables that we already came up with, right? You got true, false, 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 and you got true, 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 false. Okay. And yeah, they say what we already know. So let's try to evaluate some of these things. Or at least, work through these and make some sense of them. So this is like the questions in the textbook here. So what they're going to do is they are going to make a statement like this. Let P be the proposition, Greg's computer runs Linux. Okay, so they define a variable P. And then they define another one. Q is the statement, Greg's keyboard doesn't work, right? And so then you say, well, what are we going to do with that? Well, they want us to figure out what P and Q is. Well, you know that for P and Q, all you're going to have to do is, well, like literally take this one and then say and this one. That's all you have to do. And so that's what we do here, right? Greg's computer runs Linux. That's the P. And that's the and. Greg's keyboard doesn't work. Oh, I thought I made a typo, and then I realized that I just made a joke. Did you see my joke? Look. Greg's keyboard doesn't work. I'm funny. Dang. All right. So Greg's computer runs Linux, and Greg's computer doesn't work. P and Q. Okay. Now, man. So I'm trying to cover up the answers here. That's kind of tricky to do. So I have an idea. No, that won't work. So I'm going to not uncover the answer yet. We're going to try to do this one. So it says translate into English. Okay, so they say not Q. So how would I say not Q? So you come up here and say, where's Q? Q is Greg's keyboard doesn't work. So Greg's keyboard doesn't work. And this is the negation, right? So what would the negation of Greg's keyboard doesn't work? The negation would be Greg's keyboard works, right? The negation of doesn't work is works. And then we have this symbol. What's that symbol? Or. So you just say or. And then we have Q. Why do we have Q? Oh, that's supposed to be a P. Whoa, that doesn't even make sense. Okay, I don't know what's going on here, but this is not what that says. Actually, this is a very stupid one anyway, right? It says not Q or Q. So Greg's keyboard works or Q. Well, what's Q? Q is Greg's keyboard doesn't work. Greg's keyboard doesn't work. All right, sounds good. Greg's keyboard works or Greg's keyboard doesn't work. Yes, I agree. Those are the choices. Now, I don't know what I was writing there. I think I must have typed in the previous line, the top line, obviously I typed in wrong. So I did what I did. But anyway, so problems in the textbook are like this. They give you symbols and they want you to write English. Or they write English and they want you to write symbols, one or the other. Okay, two more logical operators. So the two that we get are exclusive or. It's another one, which a lot of times in computer science, you'll see that written this way. XOR for exclusive or. And then you've got the conditional statement, which is generally written this way. Actually, I mean, the symbols XOR is not how we're going to write it. We're going to write like this. And you don't use this one very much in this class, but here are the definitions. So exclusive or. So exclusive or versus or, right? We had or up here. So remember how or worked. So actually, let's look at this truth table a little bit. So if you have true or true, then the result is true. If you have true or false, the result is true. If you have false or true, the result is true. And then if you have false or false, the result is false. But what I want you to think about is this one, because this one, the top statement, really is not how people use the word or in real life. So like if I make a statement like this, if I say I'm going to the movies, or I'm going bowling. I don't know why we use bowling a lot, but we do. If I say this, if I say I'm going to the movies or I'm going bowling, it makes it sound like I'm doing one or the other, right? But according to the definition of or, I could be doing both, okay? According to the definition of or, this definition of or, I could be doing both. And that's not how people normally use the word, right? Like if I say I'm going to the movies or I'm going bowling, you would probably think that I'm doing one or the other, but I'm not doing both. But this mathematical definition of or, I could be doing both. So P or Q says I might do both. Okay, and that's not how people normally say it in English. Now down here though, the reason I'm mentioning that now is because exclusive or is what people actually usually mean when they say or. Because if you look at the definition here, it says proposition that is true exactly when one of P and Q is true. So that's the key there. So like the key is exactly one is true. That's exclusive OR. So that's actually how people normally mean OR. Because if I write the truth table, P, Q, P exclusive OR Q, that's crooked, I don't care though. If you write the table for P exclusive OR Q, again, true, true, false, false, true, false, true, false, and you fill this out according to the definition here, it says it's only true when one of them is true. So where is one of them true? Here, true, false, and the other one right here, false, true. And it says false otherwise. So false, false. So this is the truth table for exclusive OR. So it basically just takes out the true, true case, right? That's what's different between exclusive OR and regular OR. Okay, so that's exclusive OR. Now, the other one we want to look at is the conditional statement. And the conditional statement is the one that, we're going to spend the most time trying to learn here. Because it's kind of I won't say the trickiest, but it's just how theorems are made. I'm going to move this up a little bit. So conditional statement is if P, then Q, right? And you write it this way. So you can read this either as if P, then Q, or you could read it like this: P implies Q. It gets read that way a lot. So P implies Q. Okay, and we can make the truth table for it, which I know it's right down there, but I'm going to make the truth table anyway so we can talk about it. P, Q, P implies Q. And we got, how do we do it? True, true, false, false, true, false, true, false. And let's read the definition, right? We're going to try to read the definition. So it says, false when P is true and Q is false. P is true, Q is false. There. True otherwise. All the others are true. So true, false, true, true. And that's P implies true. Now, why is that the case? Okay. The reason that the truth table is like this is, do I have space to write words? I do, okay. I'm going to write some words down here. So I'm going to try to explain why the truth table is the way it is. So let me just make a statement like, let's see. If it's not raining, then I will go to the movies. Okay, so there's a statement, right? That's P implies Q, where P is if it's not, or P is it is raining. Maybe I'll even say it because we're not that good at it yet. So in this case, P is it is not raining. Q, that's a Q, is I will go to the movies. And I know that like maybe it's a little bit confusing to say it is not raining as P. That's not the negation of P. I'm saying P has the not in it for not raining. Okay, so then the statement is P implies Q. If it is not raining, then I will go to the movies. Okay, so that's P implies Q. So if you think about the four cases are as follows. It is not raining. and I go to the movies. Okay, that's one case. Now, if it's not raining and I go to the movies, was I telling the truth here? If I say if it's not raining, then I will go to the movies, and it's not raining and I go to the movies, then I'm telling the truth there, right? So I'll say that that's true. Now, if I say it is not raining and I don't go to the movies, right? Well, look at the statement. I said, if it's not raining, I will go to the movies. And it's not raining and I don't go to the movies. If it's not raining and I don't go to the movies, then I was lying up here, right? The blue statement is a lie. And that's what makes this false. Okay. Now, the other two choices are a little bit confusing. They say it is raining. And the other one said it is raining. And then the two choices are I go to the movies and I don't go to movies. Now, the whole key here behind these two is they start out, it is raining, it is raining. And if you look at the statement, the original statement, I say, if it's not raining. So I said, if it's not raining, then something. Well, I only made a statement about what I was going to do if it was not raining. I didn't make a statement about what I was going to do if it is raining at all. I said what I was going to do if it's not raining. So these last two choices where it is raining, I never said anything about it, one way or the other. And that's why this comes up true. So this comes up true and this comes up true. And the whole reason is it's raining. And the original statement didn't say what happens in that case. So I never said what happens if it's raining. Right? I only said that if it was not raining, I was going to the movies. Okay, so that's a little bit tricky. It's a little bit confusing there that this is almost the same kind of thing. Maybe, I don't know if we're going to do this one. But, so, do you see how that works for the conditional statement? It's a little bit confusing. So the reason these come up true is because you said if P. But in this case, P is false. So you said if P is true, then something. But if P is false, you didn't make any statement at all, and that's why those both come out true on the conditional statement. And even if it doesn't make 100% of sense to you, you can look at the truth table and see how it's supposed to work out. Okay? And yeah, okay, so it says if it rains today, then I will stay home. I don't need to cross that out. That's a conditional statement. So, okay. Now, something that you're going to have to do, and so I printed it here. It's in the book, of course. I copied this from the book. But there's a million different ways to say P implies Q. And here they are. So all of these are P implies Q. All of them are P implies Q. They're all the same, even though they look different. So, you know, if P then Q. Sure, that's the main one, right? Then you've got P implies Q. Well, I say that a lot too. Then you've got this one, if P, Q. Well, they just left out the word then. So that still makes sense. It still says if P. This one's confusing. P only if Q. This one's very confusing because it says you see the if next to the Q. And so that makes it easy to get backwards because you say, oh, it says if Q. No. It says P only if Q. So you've got to recognize which one's which. And when I say you have to recognize it, I mean that because like you need to be able to look at this and understand that the symbols for this is actually this. And it's really easy to get backwards because you see the if on the Q. Okay. Now, the next couple are going to show you something. So in this statement here, I'm going to say P implies Q. And it says P is sufficient for Q. And here it says a sufficient condition for Q is P. So in both cases, notice that when it says sufficient condition is P, right? Like a sufficient condition is P. Now it says for Q, but what are they describing as sufficient? They're describing P as sufficient. And here it says P is sufficient. So they're describing P as sufficient. So this is called the sufficient condition. And the Q is called the necessary condition. Yeah, and the reason that's the case is because if P is true, that's sufficient to make Q true. And if Q is true, then it's necessary that, wait, is that right? Hold on. Let me think about the way I'm saying that. So P is sufficient. So if P is true, that's sufficient in order to make Q true. And if Q is true, it's necessary that P is true. If Q is true, then it's necessary that P is true. And it's tricky to talk about, but what you can do is just remember this. I say P is the sufficient, Q is the necessary. And so you would be able to read a sentence like this, and then you would just be able to say, it says a necessary condition for P is Q. What is necessary? The Q is necessary. Q is necessary, right? Because the whole point of being able to read this is being able to tell which one's the P and which one's the Q. And so if it's necessary, it's Q. If it's sufficient, it's P. And even if you don't like the wording, you still need to be able to recognize it when you see it. So if they say sufficient or they say necessary, what's that mean for P and Q? Okay, and so there's just so many different ways to write these that they're hard to translate, but that's why we're printing them all here. Yeah, okay. So conditional statements is to think of them as a contract. So if you say, if I'm elected, I will lower taxes, right? The only time it's false if I'm elected and don't lower taxes, right? Because I'm making a statement about what I'm going to do if I'm elected. If I'm not elected, well, obviously I can't lower taxes, right? So I can still be telling the truth when I say if I'm elected, I will lower taxes. Even if I'm not elected, that doesn't mean that I'm lying. That just means I wasn't elected, so I didn't have a chance to lower taxes. Okay, and so that helps understand how a conditional statement works, right? Again, that's why if the first part is false, if I'm not elected, then the statement is automatically true because I never said anything about what would happen if I was not elected. Okay, this lecture is going kind of long, but we still got more stuff to do. So let us get to it. So there are things related to conditionals. So you've got an original conditional here, right? So we've got this original thing, P implies Q. And then you've got a converse. What's a converse? Converse means switch them. So the order switches. So if you switch them, that's converse. Okay, now inverse means something different. Inverse means, look, there's a negation and a negation, right? So not P, not Q, right? And the last one, contrapositive, is this. So this one, you negated them and you switch them for contrapositive, right? So if you're trying to write converse, inverse, contrapositive, then what you've got, I'm going to erase these actually and write them again, or write them a little bit different. So there's like two things you can do basically. So converse, you switch the order. Inverse, you negate, but you keep the same order. So you add not on both of them. And then contrapositive, you switch order and negate. Okay, and the reason you care about these, by the way, is because in mathematical theorems, you can talk about the converse and the contrapositive and so on. And so they'll make a statement like they'll say something like this. If let me say, like if n is odd, then what do I want? Actually, I wanted this. If m and n are odd, then m plus n is even, right? That's a statement. It happens to be true, but the converse is not true. The converse, what's the converse? M plus n even. If m plus n even, then m and n are odd, is false, right? But I said if m plus n is even, then m and n are odd, right? I had to write that out for you, but I didn't have to write it out, right? I could have just left this all out, and then I could just say the converse is false. And if I say the converse is false, you would have to know what it meant. Like, what's the converse, right? I say the converse is false. So you would have to know that the converse is switching the order, but nothing else, not negating anything, switching the order. It's false. So the converse is false. The contrapositive, by the way, is true. I'm not going to write it because we're going to talk about it a lot more later on, why that's true. But the contrapositive of a true statement is always true. So that's why I can say that for sure. All right. So something that happens a lot is you need to be able to say that P implies Q and Q implies P. Right? So basically which way the conditional goes is both ways. And so that's why they would call it a biconditional. So if P implies Q and Q implies P, then it's a biconditional. Okay, and we write it with symbols that make sense. The arrow goes both ways. So P arrow to Q, Q arrow to P. What's the truth table? Well, the biconditional here is going to be true when they have the same truth value. So what we're looking at for a truth table, P, Q, P, if and only if Q, probably says that somewhere. Yeah, it does. If and only if Q. How is the truth table? True, true, false, false, true, false, true, false. And what is it? True when they have matching values. So true, true should be true. False, false should be true. And on the other two, they don't match, right? True, false, false, true. Those are the two that come up false. Okay, and that's the truth table. So when you say if and only if, you're saying that they're the same. They're the same. So P and if and only if Q means both true or both false. Okay, there it is. There's the truth table. Okay, so precedence of operators. You are not going to use this basically ever. However, if you need to do it, then this is the kind of the order of operations that you would do it. Now, the reason you have this kind of thing is because if I write this, so like if I write not P and not Q like that, you're supposed to understand since this is priority 1 or precedence 1, then that's the same. Not P and not Q, right? And so if you know the precedence, then you don't need to use parentheses around the not P and around the not Q. And that's what this is for, is to avoid, in order to avoid having to write parentheses as often. And so the negation is the highest priority, so you would evaluate the negations first, then you would evaluate the and or the ors, and then finally you would evaluate any kind of conditionals. And they don't usually leave it to chance. So like when they're mixing these two, they'll use parentheses so you don't have to know this precedence thing, right? Because it's just bad form to write something like this, right? P and Q implies R, for example, right? Because it's either P and Q parentheses implies R, or it's P and Q implies R. And those aren't the same, right? So which one is it? Well, according to the precedence, you should do the and first. And so that would make this one the correct one. But again, they would generally use parentheses rather than making you figure that out, okay? Because it's just too hard to remember those. I mean, it's not hard, but it's confusing to write. It's not a good way to write it. Okay. So something you're going to need to get good at, or at least okay at, is writing truth tables. Okay. Now, so let's write a truth table for a complicated statement here. It's not that complicated. So when you're trying to write a truth table for something like this, what you would want to do is do it the way we did all the other truth tables. So you're going to make a table. But what you're going to put in it is, well, what do we have for different variables? We have a P, another P, and a Q. So overall, what do we have? A P and a Q. Okay? So we have a P and we have a Q. Now, how are we going to work this out? Well, you don't want to have to do something too complicated in your head. So you break it up into pieces. So like what I would do is I would say, okay, well, we're going to need to know what this is. We're going to need to know what this is right here. So the way we'll do that is, let's first write out what not P is, because I see a not P. And then once I have a not P, I should be able to work out what not P or Q is, right? Because the not P and the Q are these columns. So if I have both of these columns, I should be able to do this column. And then once I have this, then I should be able to look at this column and the original column and figure out what P or not P or Q is. And so the more columns you write, the easier your work will be. But of course, the more writing you have to do. So just keep that in mind here. So let's try to do this. So since I have two propositions, we'll start out the same way we've done this a bunch of times. True, true, false, false. And then true, false, true, false. Okay. Now what you're going to do is you just go column by column here, figuring out what these are based on what you know about truth values from all these truth tables that we had up here that we learned. So like this column is not P. How do you get the column not P? You're going to look at the column for P and you're just going to negate it. So we just negate the column for P. So if P is true, then not P would be false, right? And here, if P is true, then not P would be false. And if P is false, not P would reverse it and it would be true. And if P is false, then not P would be true again because we would reverse it. And now you've got another column. Now you've got another column in your table. So then we move on. We'll do the next column. So in order to do this, not P, so we have this right here, not P, which is this whole column. But then you have Q, which is this whole column. So we need to look at those two columns that I highlighted and figure out how to do an OR between them. Now, in order to do that, you need to know how OR works, right? Because this is OR. So you look back up at your truth table for OR, or your definition for OR. Where is it? Way up here. Way up here. OR. Here it is. So the way OR works is this. When it's false and false, you get false. Right? False or false, you get false. So as long as there's at least one true, you get true. Right? There's a true, you get true. There's a true, you get true. But if it's false or false, you get false. So any trues give you true, but two falses give you false. And that's how OR works. So you come down here and you say, okay, well, where's our table? Way down here. So just do this line by line. So we have true or false. True or false should be true, right? And then we have false or false. Well, false, false was the only one that comes up false. And then we have true, true. True or true is true. And then false or false is true, right? The only time you get false is when you have two falses. So this is not the same order, right? Like the order here, true, false, true, true. That's not the order we had up here. Wherever it is. Yeah. That's not the order we had here because we didn't have the trues and falses in the same order. What you needed to know was that false, false gives you false, and everything else is true. So false, false gives you false. Where am I? Make this smaller. So false, false gave me false, and everything else was true. Okay, so you have that. Now once you have that done, then we need to evaluate the last column. So the last column is going to involve P, which is way over here, and also this one, which is this one. So that's the one we did. So we need to look at these two columns and we need to work out an OR between them. Is it an OR? It is an OR. So let's do that now. So we're looking at the green and the yellow highlighted columns. So what do we do? First row, we have true, true, true or true. That's true. Then we've got true or false. Also true, right? Remember, the only time an or is false is when it's false, 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 false. False, true. That's true. False, true. That's true. So there you go. There's my truth table. There's my truth table. Interesting. It came up true, 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 true. 4 truths. That's fine. That's perfectly fine. But that's how you do this. Do you see? So you go column by column, build up more complicated things from the simpler things. All right, let's do one more, and I think we'll be done after this. Hey, there's paper at the end. Man, it wasn't letting me do this earlier. I thought that's why I kept writing on when I didn't have any space, because I didn't know I'd have more paper at the end. All right. Anyway, let us continue. So we need a truth table here for this one. P, Q, P, R. Now, notice that we have 3 different propositions. We haven't done some... Sorry. Sorry, just trying not to choke to death here. But I can't stop this because I'll have to start the whole thing over. All right, let's go. So truth table here. So with 3 things, we know that 3 propositions is going to mean 2 to the 3 rows. So 8 rows. Okay, so we have 8 rows in our truth table. Now, what you're going to do is start out making your truth table the same way as always, and we're going to go P, we've got a Q, and we've got an R. Okay, so we have P, Q, and R. Now, then what we're going to do is we need to build up this statement here. So the statement that you have here is, I think the first one we're going to do is going to be P implies Q. Let's do that. What are we going to need? We need, it looks like, a not P. Let's do a not P. Next to it, you have a not R. No, we don't. Okay, yeah, we're fine. Okay, so at this point, we should be able to go to, I guess, not P implies R. And then finally, the whole thing, P implies Q, or not P implies R. Okay, so that's how we're going to do this. My lines are not very straight, but that'll be okay. Now, since we haven't done one with 3 before, here's how you would do it. So there's 8 rows total. So when you have 8 rows total, what you want to do is kind of the same thing we did before, but a little bit different. What you want to do is for your first proposition, instead of 2 and 2, you want to go 4 and 4. So that means we'd go true, 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 true. 4 trues. Then 4 falses. False, 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 false. There's your 8 rows. 4 true, 4 false. Then the next proposition, you go 2 and 2. So you go true, 2 trues, followed by 2 falses, 2 trues, followed by 2 falses. And then for your third proposition, you go 1 by 1. True, false, true, false, true, false, true, false. Okay, and I'll add an extra line in here just to kind of help me keep track of what I'm doing here. A couple extra lines. Okay, so that's how you do it. Do you see? 4 trues, 4 false, and then 2 and 2, and then 1 and 1. And that pattern there will cover every possible combination of true and false. And that's why we're doing it, to get all the combinations of true and false. Okay, so let's try this. Actually, now that I've done this, realize I kind of just want to do the entire thing in a grid. I really wish those red lines were straight now, but they are not. Wait, you know what? We have this power. Well, I still can't make it straight because I'm not smart enough. I'm letting down the side, man. Okay, well, I'm not making it better. I am not making it better. But I am done. So the green lines are crooked too, I realize now. Okay, anyway, so let's try to do this. So we're going to do this one by one down here. There's one we can do pretty quick, right? Let's do this. So I see this column here, not P. Let's fill out not P. So not P is the negation of the P column. So the P column was the first column. So true, 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 false, 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 false. So we're going to go negate that. So it's going to go false, 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 true, 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 true. All right, so that column is pretty easy actually. Then let's do this one. So we've got a P, which is here. We've got a Q, which is here. And we need to do P implies Q. So you have to remember what the truth table looks like. And so the truth table for conditional, because that's a conditional, is here. Conditional. So look at this. The only time it's false is when it goes true, false, right? True, false gives you false. True, false gives you false. Only time. So we come down here and we're looking for that. True, false gives you false. And we'll mark those as false. So you just come here and you go, okay, well, this is true, true. That's true. Another true, true. It's true. True, false. Wait, true, false gives you false, right? So this is false. Another true, false. That's another false. And then the rest, false, true. That's true. False, true. That's true. False, false. That's true. False, false. That's true. Remember, if the first one is false, then we're not making a statement at all, really, right? Because we're saying if P, then Q. But without P, then we're not saying anything. All right, so we did that. Next one. So not P implies R. Now, so what's tricky about this, not that tricky, but what's a little bit tricky is that you have not P. Not P is right here. You have R. R is way over here. And the thing is, though, that not P is on the left, but down here it looks like it's on the right. Right? So remember, this is the left side, this is the right side according to this. So let's figure it out. Let's do it. So this is false. False implies true. False implies true is true. False implies false, true. False implies true, true. Remember, it's only true, false is the only time that you get false. False implies false, true. True implies true, true. True implies false. Aha, that's a false. True implies true. True. True implies false. That is false. Oops. Okay, last one. So we're almost there. Is it supposed to be false? Okay. So now we've got P implies Q. Where's that? Here. And then we've got not P implies R. That's here. And it's an or between them. So remember, or is true whenever either one of them is true. So any trues make this last column a true. So we've got true or true, that's true. True or true, that's true. False or true, true. False or true, that's true. True or true, that's true. True or false, that's true. True or true, that's true. True or false, that's true. Okay, so we got another column of all trues. Now that does not normally happen. Like, you see how these both came up, all trues? There's no reason in general to expect that to happen at all. Okay, no reason at all. Okay. Now something I do want to show you though is that you can check your answers here pretty easily. So the way you would check your answers is if you go to a web browser. I'm kind of failing to do that now. You can't see it on your screen, but I don't know how to use an iPad. Okay. So you could actually check this in like Wolfram Alpha is how I would recommend it. So take a look at this page, Wolfram Alpha. You're probably familiar with it because you guys have taken a lot of math classes, but you can try to write this. So I'm going to try one way that may or may not work. Some things understand this to be an arrow. So a dash and then like a greater than symbol. So I'm just going to write this out. P implies Q. Or, now we don't have an or command, right? So I just type in or. Then I say, how am I going to type in the negation of P? You just say not P implies R. So that's how I would type that in. P implies Q or not P implies R. When you type this in, it probably will give me the truth table. If it doesn't, I'm going to ask for the truth table. So I'm just going to hit enter. It didn't like it. Okay, let's ask for the truth table. Truth table. No, it doesn't like it at all. I know it can do it. Come on. Just let me put the cursor where I want it. Man, I know for a fact that you can do truth tables here. Why is it not letting me? All right, we'll make it do a truth table somehow. Come on, you're joking here. I'm just going to check this real quick. Okay, that's what it doesn't like. Oh, it uses, oh look, it uses equal. It uses equal for the arrow. That's what it didn't like. Okay, sorry. let's do this. This is going to work. I am like 60% sure that this is going to work now. It wants that for the arrow. Okay. And I can still make it a little bit nicer, so if it doesn't like this. Aha, it did. So a couple things I want you to note about this. So first of all, you see how to do not, you see how to do or and. You see we got the right answer. True, 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 true. It does not give you the entire truth table that a person would have to do because it doesn't show its work. So it only gives you the first 3 columns and then the last column. Also notice that they followed the same pattern that I said, right? Like the P goes true, 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 true. The first column, true, 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 false, 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 false. And then true, true, false, false, true, true, false, false for Q. And then R goes true, false, true, false, true, false, true, false. So that's the exact same pattern that I did, right? And that's because that's how everybody does it, okay? That's why you can just look at the answer and know that we have the right truth table. If they did it in a different order for P and Q and R than me, then it would be really hard to compare the truth tables. And that's why people are very standard about how to do this. However, I do know that, like I said, in other programming classes at Merced College, you may do these in a different order because if you fill out your truth tables with the zeros and ones, there's another order that makes sense other than the one that we used. Okay, so I think that's everything I wanted to go over. This is an hour and a half, so probably plenty. You probably are going to have questions about the homework, okay? So when you have questions about the homework, come to office hours and I will be happy to help you with anything in the homework, okay? And yeah, and there will probably be some supplementary video if people send me questions where I will record solutions to specific questions and post those to help you with the homework. But still, come to office hours and ask your questions, and that's the easiest way to get help. Okay, so that's it for now. I will see you guys later.